Go ahead and get started. Get some people rolling in. Hi, everyone. Welcome to another CMU session on differentiable physics. Today, I'm happy to introduce Dr. Vikas Sindhwani from Google Brain as our session chair. Vikas received his PhD in computer science from the University of Chicago and previously led a team of researchers in the machine learning group at IBM Research. Today, he works as a research scientist at Google Brain, where he leads a group focused on solving a range of perception, learning and control problems arising in robotics. His interests are broadly in core mathematical foundations of statistical learning and in end-to-end design aspects of building large-scale, robust machine intelligence systems. So thanks very much for joining us today, Vikas. Very glad to have your perspective for the session. And I'll hand it off to you to introduce our speakers.
Thank you. So firstly, thanks a lot to the organizers for inviting me to participate in this webinar. Today's theme is differentiable physics for robotics. That's an area I'm really excited about in terms of enabling physics engines to interface with machine learning systems and also with state-of-the-art automotive engines that can exploit accelerator hardware. So as you know, at Google, we think a lot about scale, and we feel like that's been the key to sort of advancing vision, natural language processing, and speech. And for various reasons that we are all familiar with, collection of large-scale data for robotics seems to be fraught with lots of challenges. So if we can get simulation to be as realistic as the real world, we can hope to use the same recipes. So today's speakers are Taylor Howell and Simon Luke-Kliat. I hope I got the pronunciation right. I consulted with Vincent on the accent. So they're both graduate students at Stanford. We hosted Taylor as an intern in our group last summer. I think we had a very productive time. And we're excited to host Simon this coming summer to also work at the intersection of physics and learning. Taylor received his bachelor's in mechanical engineering in 2016 from the University of Utah and his MS in mechanical engineering from Stanford in 2019. Simon received his master's in mechanical engineering from Stanford in 2019, and their shared interests are in simulation, optimization, and control for robotics, particularly in systems involving contact. So with that, I'll turn it over to you guys.
Thanks a lot for the nice introduction, Vikas. So we're going to go ahead and share the screen. And also thanks to the organizer for setting this this seminar up. This is an incredible opportunity for us to talk about the work that we've been doing. So I'm Simon, and this is Taylor, and together we worked on a differentiable physics simulator called Dojo. And this physics simulator is targeted at robotics applications. So today the team we are just Taylor and I are presenting this work, but this is a larger team that has been working on this simulator. We have also collaborated with Jan Brudigam from TU Munich, Zico Coulter and Zachary Manchester from CMU, and Max Schrecker at Stanford.
Okay, so with Dojo, we designed a physics engine that prioritizes two things. The first is physical accuracy. So with a bunch of algorithmic improvements and modeling choices, we're hoping to better capture the physical world and contact interactions. And the second thing we prioritized was differentiability. So returning useful gradients for things we care about, like states of the system, actions, with respect to system parameters like mass and inertia, contact parameters like friction coefficients, and even things like the time step used in the system. So with Dojo, we have worked on a bunch of applications and little examples. So in the top left here this is an Atlas model. We're taking the arms off. So it's basically a biped system, but using ILQR, we've been able to produce this multi-step walk. And we're able to optimize this trajectory in basically 10 to 20 minutes on a pretty standard workstation. Next to it on the right is a quadruped. This is a unitary A1 robot. Similarly, we used iterative LQR to generate this gate. We can also simulate a bunch of interesting physical phenomena. So in the right-hand corner, this is the tennis racket effect. So we're able to capture things like unstable rotational motion about an object's second principal moment of inertia. Right below it, this is a tippy top, which has similar physical phenomenon, but here it's interacting with the surface, so there's friction and impact. And the tippy top will basically oscillate between two modes. We can also optimize trajectories for classic systems like the cart pole in the bottom left-hand corner. So we're able to optimize the swing up trajectory. We also implemented a number of OpenAI gym-like environments. So in the bottom middle, this is an ant environment, and we're able to use Dojo to train policies for locomotion using reinforcement learning. And then finally, we are really interested in our group in simulating robots that we've designed with custom hardware. So in the bottom right, this is what we're calling the Rex hopper. So it's a little monopod hopper that someone designed in the group.
Yeah, so we are developing a new physics simulator, and you might be wondering why we need to do this. So there are already plenty of very good physics simulator out there, like Mujoko, Drake, Bullet, or Brax developed by Google. So those physics simulators are really good. For example, Brax is very, very scalable to large compute. And Mujoko has been developed for more than 10 years. So they are very good simulators, but they also have some limitations. So we are going to go through some of them here. So this is a list of the popular simulators. And if you look at the application column, so what is the target of the physics simulator? Some of them are targeting the graphics community. So trying to get, in this context, the objective of the simulator is to generate behaviors that looks correct to the human eye and are not necessarily very accurate in terms of the physics simulation of the dynamics. Other simulators are also using soft contact model. This is the case especially for Mujoko, which is a famous simulator for in the reinforcement learning community. And soft contact models are typically not capturing very well the behavior of real-world robots. So because they are built with rigid bodies mostly. So this is one of the limitations of Mujoko. And finally, in the last 4 years, we have seen many simulators coming out, providing gradients, so differentiable physics simulator. Mujoko has a finite difference scheme, which is providing informative gradients to optimizers that are built on top of the simulator. But this is pretty inefficient in terms of computation. This is requiring a lot of compute to get the gradients. Drake has proposed another method, which is a gradient bundle approach. We might be able to talk about this at the end of the talk, but this is also pretty inefficient in terms of compute. And more recently, there has been development in terms of providing subgradient information. So basically differentiating the simulator and providing subgradients. Those gradients are typically, we found that they are not extremely informative for the downstream optimization tasks. So if you want to do trajectory optimization and you're using subgradients information, this is going to be challenging task to optimize your trajectory. So what Dojo is doing in this case for providing gradients, it's providing a smooth gradient that is a bit different from the subgradient, and it's also analytical and fast. So yeah, we think that Dojo is kind of uniquely positioned, targeting robotics applications, simulating hard contact that is capturing well the behavior of rigid robotic hardware and providing smooth and cheap gradients for downstream optimization tasks like trajectory optimization, policy optimization, reinforcement learning, or system identification. And we are going to cover all these applications later in the talk. So this project, this physics simulator, Dojo, we've been working on this with Taylor for about a year now. And we've tried to make it as general as possible and as reusable as possible, so that people can build on top of it. We see it as a building block, so you can build many other applications on top of it, like reinforcement learning applications or policy optimization, for example. And to make it even more accessible, we have written a Python wrapper called DojoPy. So the main package is written in Julia, and then we have a Python wrapper around it. And so this Python wrapper is providing an interface to the environments and the robots that we've built in the simulator that is looking a lot like OpenAI Gym's environments.
There's a question, if I may interrupt just for a second, about elaborating on the difference between soft contact and hard contact and the impact on physics / differentiability.
Yeah, so this is, I think, a really good question. Basically, hard contact is inherently non-differentiable. It's non-smooth, potentially discontinuous, whereas a soft contact model, because of the inherent softness and continuousness of the dynamics there, makes it easier to differentiate. So with the soft contact model, I guess the Dojo developers basically decided if we have a soft contact model, we can differentiate through it and potentially get good gradients. And so with Dojo, we're basically able to simulate hard contact, but we are able to return smooth gradients as if we had a soft contact model. And we'll talk more about how we do that and kind of some of the trade-offs a bit later in the talk.
Oh, we can't hear you, Vikas. I'm sorry.
So I have to unmute myself. One more question. Is the smooth gradient realized by the auto-lift feature of Julia? Why not write it using Python? Is it because Julia is faster?
Yeah, so really good question here. So we are not using the auto differentiation feature of Julia to provide the gradients. We are using the implicit function theorem, and we are going to give a lot of detail about this. But basically, yeah, the simulator is solving an optimization problem, and we are going to differentiate through this optimization problem by using a classical method called the implicit function theorem. Yeah.
I had one question from my side, which, as you know, I'm a big JAX enthusiast, and I was wondering, basically, is DojoPy just providing custom gradients to the core dynamics utilities that are implemented in Julia, and whether other JAX features like VMAP and things like that can also be used? So from a JAX perspective, it's a black box.
Yeah, so with the JAX, currently what we have implemented is like a custom vector Jacobian product rule. So you can basically differentiate through it. I haven't added the support for like VMAP or PMAP yet, but this should be something that we can easily do. I guess one other thing I can say too is, while we're not using any of Julia's auto diff or forward diff features, this is something where we can basically overload chain rules so that Dojo automatically works with these tools, just like it can automatically work with JAX once we define custom differentiation rules. Okay, so in the rest of the talk, we're going to break down into 5 sections. So we'll talk about Dojo's maximal coordinates representation that is a little bit non-standard, but is potentially really useful for robotics. We'll talk about variational integrators and how we have better energy and momentum conservation using this. We developed a custom higher fidelity contact model that we'll discuss. And then to make all of these features and algorithms work, we devised a custom interior point solver that can reliably solve the contact problem, and we can differentiate through to get smooth gradients. And then we'll discuss how we actually efficiently compute these smooth analytical gradients. So the maximal coordinates representation, one of the motivating examples for this is the ability to simulate tricky mechanisms. So a lot of robotic systems have these closed kinematic loops. One example of this is a 4-bar linkage that you can see on the left. And in practice, what happens when you close a kinematic loop, it basically introduces numerical ill conditioning to your simulation. So in practice, what a bunch of solvers do is they have some sort of PD controller. It's basically pinning one of the joints together. And this is a little bit ad hoc. It requires tuning by the user potentially. And a lot of the times your simulation will go unstable and the simulation will kind of blow up. And these mechanisms appear in all sorts of robots that we might want to build. So in the middle, we have a Rex hopper that someone in our group designed, and it actually has a 5-bar linkage. And so we want to be able to simulate this. And with maximal coordinates, this is pretty trivial to do, and we can handle these kind of closures really nicely. So if you're kind of unfamiliar, what is the difference between, like, what is maximal coordinate representation? You're probably familiar with a minimal coordinate representation, where, for example, on the quadruped, we're going to represent the floating base or the body of the robot using a position x. It's going to have linear velocity v. It's going to have some orientation q that's quaternion, and then it will have some angular velocity omega. And then for each of the joints in the robot, we're going to add 2 additional states. So there's basically the position of the joint and then how fast the joint is moving. So theta and theta dot. And then we'll have this extra 2 states for each joint in the robot. And we'll end up with a state representation that's something like 37 dimensions for this quadruped. Now, in contrast, in maximal coordinates, it's going to be a little bit different. So the floating base is going to have the same representation as before. But now every rigid body that's part of this mechanism, we're going to give the full representation. So it's going to have an x2, a v2, a q2, and an omega2. And we're going to do this for every single body in the mechanism. And now the result is we have a way larger state dimension. So for the quadruped, it's 169 states, which is way, way bigger. And you might be thinking, you've made the problem way harder unnecessarily. Why would you do this? And what actually happens is this introduces a bunch of sparsity and structure into the problem. So behind the scenes, when we perform simulation, at the very core is an AX equals B linear system that we need to solve. And this is that A matrix. And you can see the sparsity. It's super sparse. There's a bunch of structure. And we have a custom LDU linear solver that can exploit all of this and really efficiently solve these systems. So with a maximal coordinates representation, we can still be basically as fast as a minimal coordinates representation by exploiting all this sparsity. But now we can also add all sorts of constraints on our system to have closed kinematic linkages, which is really nice for handling contact in maximal coordinates. This is much nicer. We don't need to be propagating contact forces through a kinematic chain, which can introduce error accumulation over time or up the chain. Yep, so with maximal coordinates representation, we can essentially simulate way larger systems still really efficiently.
Yeah, so this was for the maximal coordinates representation. Another feature that we wanted to talk about for Dojo is the variational integrator. So how we integrate the dynamics through time. So basically, how we can compute the configuration or the position of the robot at the next time step. given the current position and velocity of each of the links and the current controls that are applied on the motors, for example. So variational integrator, it can be super useful, especially for applications where you want to have good conservation of linear momentum, angular momentum, and energy of each of the robots or objects in the environment that you want to simulate. So, for example, for space applications, this can be extremely important to make sure that you're not pumping in energy or pumping out energy of objects in the scene, so that you have an accurate simulation. So there are like different type of integrators to integrate dynamics. Some of them are explicit integrators like Euler integration or Runge-Kutta integration schemes. And the way we usually derive those integrators is that we first write down the least action principle in continuous time. Then we apply the Euler-Lagrange equations that operate on the Lagrangian of the system, and this gives us the usual dynamics equations that we are all familiar with. So F equal ma, so the force is equal to the mass times the acceleration. This is for a particle, for example. So this is the dynamics of the system in continuous time, and then once you have this, you discretize the time dimension, and you get you can get this integration scheme. So in this case, it's just Euler integration. The position at time step t+1 is equal to the current position plus some time step times the velocity and some acceleration term. So this is Euler integration. This is the classical thing, but it has some issues, especially with conserving energy, momentum. It's also not a stable, not a stable integrator, especially when you have stiff dynamics, which is the case for contact dynamics. So what you can do instead of using the Euler-Lagrange equations and then discretize, you can do it the other way around to get a variational integrator. So you take your least action principle in continuous time, you discretize it across time steps into this discretized least action principle, and then the next step is to use the Euler-Lagrange equation on this discretized least action principle. And what you end up with is an integration scheme which is implicit. So instead of explicitly computing the position at the next time step, p plus, it's an equation that you have to solve for to obtain p plus. So it's trickier to solve. It requires to use Newton's method typically, but the benefit is that you get some nice conservation properties. You get in our case we get conservation of the linear and angular momentum of robots, and also conservation of the energy of the robot. So one of the benchmarks to evaluate this kind of the conservation of those quantities is this astronaut environment, where you have the humanoid taken from the Mujoko environments. And it's floating in free space. There is no gravity and no contact with the ground. And we simulate that for a certain amount of time, starting with some initial velocities on each of the links. We simulate this forward, and we measure at each time step the amount of linear momentum and the amount of energy that the system has. And so this is the results that we get with Dojo. Dojo is in blue, and we compare to Mujoko in orange. So on the right column, you have you have the results for the momentum. So if you look at the result, we have almost perfect momentum conservation, basically up to machine precision with Dojo. And if we compare to Mujoko, which is using several different integrators, but I think in this case it was using a Runge-Kutta integration scheme, the momentum is not conserved nearly as well, which is one of the difference that sets apart variational integrator from usual integrators. We have also tested the energy drift in the left column. So we initialized the system with the astronaut system with some energy, and then we simulate forward with different frequencies of simulation. So Dojo is at the bottom. There is no drift in terms of energy. Mujoko is also doing a very good job when we use a large simulation frequency, so 1000 Hertz. But as soon as we move towards lower frequencies, especially like 100 Hertz and 10 Hertz, the simulator is starting to pump energy into the system. And so if you look at the actual simulation of this humanoid robot, you will see that some of the smaller links with less mass and less inertia are going to start to spinning really fast, and this is going to be diverging after some amount of time. So here we simulated for 2 minutes, and we've seen some failures, especially simulating at 10 Hertz, which is not the thing that you usually do. But all right, so basically with this variational integrator, we've been able to enforce those conservation of momentum and energy, and this is enabling us to simulate complex systems in a stable fashion without pumping energy in or artificially damping the system.
Okay, so one of the most important parts of a simulator for robotics is the actual contact model. And a lot of the simulators out there today, they make a bunch of approximations to the contact model. And the result of these approximations is typically unphysical behaviors. So if we think about friction, one of the common things people do with friction models is they approximate the friction cone. And on the left, you can see we've simulated these boxes sliding on a surface. And when you approximate the friction cone, you can get some weird velocity drift during sliding. Another approximation that people make for the impact model is using soft contact. So on the right, you can see we're dropping, it's a humanoid model in Mujoko. And if you look at the feet, when we drop the robot from about a 1/4 meter in the air, it actually sinks through the floor a couple of centimeters. And this is a result of the soft contact model that isn't able to handle a sort of heavy robot impacting the floor. So we'll first talk about the friction model. Intuitively, a friction model is trying to minimize kinetic energy. So it's trying to pick a friction force that directly opposes the velocity vector of your contact point. And then there's a constraint that this friction force, it has to remain within a friction cone. And a really good model for this friction cone is a Senkemoto cone, a Lorentz cone that you can see here. And what you notice about this cone is that it's really smooth. And this enables the friction vector to point in any direction in order to minimize the kinetic energy of the system. Now, what is a really common approach is to approximate that friction cone using a pyramidal approximation. And typically this is done to formulate a linear complementarity problem, or LCP. This is used as the default friction model in Mujoko. This is used in Drake. And the reason they do this is it basically introduces linear constraints, which are easier to optimize. But the downside to this is you now have this pointy friction cone, and it basically biases the friction vector to the vertices of this friction cone. And as a result, the friction force might not directly oppose the velocity of your system. And that's how you get this kind of weird velocity drift during sliding. So with Dojo, instead of using this approximation, we use a bunch of ideas from conic optimization to exactly handle the nonlinear friction cone that you see on the right. Now, as a consequence of being able to use that full friction cone, we get better friction fidelity. So in magenta and orange, we've implemented these linearized friction cones. And you can see what happens is we throw this box onto a surface and it slides a bit. And we actually get this weird unphysical drifting to the left, or I guess up in this image. Now, Mujoko also has a nonlinear friction cone that's shown here in black. And the difference with Mujoko is that they're basically only approximately solving their optimization problem using an iterative solver. And so there's also these numerical artifacts that basically result in unphysical sliding. And with Dojo's nonlinear cone, we're handling it exactly and we solve it exactly. So we get this better perfect sliding behavior.
The second part of the contact model that we have in Dojo is trying to model impact interactions between objects and the environment. So in this chart, you can see that we are trying to simulate a box falling on the ground. So it's a pretty simple system to simulate, and the thing that we want to look into is the sign distance function. So the function that measures the distance between the box and the floor. And this sign distance function has to remain positive. So this is one constraint that we have when we solve the dynamics, the contact dynamics. We need to enforce the fact that phi is larger than 0, so that we avoid any interpenetration with the ground. The second thing that we also have is that when we are making contact with the ground, we want to have forces applied onto the box, so that we make sure we are not going to go through the floor at the next time step. So this is what you see. Gamma here is a force applied on the object by the floor, and it's a repulsive force, so it has to be positive because we cannot have contact forces that are going to attract the box towards the floor. So we have two constraints, and then we have one final constraint, which is this complementarity constraint. Gamma times phi is equal to 0, and this is encoding the binary switches that you have between the two modes, in contact or not in contact. To be more precise, so when you have more concrete, when you have gamma positive, so you have some repulsive forces applied to your to the box, you necessarily have to have phi is equal to 0 to respect the complementarity constraint. So this means that when you have forces applied by the ground on the box, you necessarily need to be in contact. The contraposition of this is that when phi is larger than 0, so when the box is up in the air, you need to have gamma equal to 0. So this means that you have no force applied by the ground on the object. And so this is what Dojo is simulating internally, trying to enforce those three constraints. It's a challenging task to do because complementarity constraints are challenging to solve for with the usual optimization tools. But in the end, the result is the following. With Dojo, we can simulate hard contact reliably. So on the left, you have the Atlas robot dropped onto the ground, and you have absolutely no interpenetration with the ground. On the left, you have Mujoko with slight penetration of the ground. So yeah, this was the constraint that we need to solve for to correctly simulate impact. And Taylor talked also about the friction. Internally, what Dojo is doing to solve for this constraint is that it's trying to it's using an inter-point solver. So I'm just going to give a short refresher about inter-point solver and how we are leveraging this tool inside Dojo to simulate to enforce those impact constraints and friction constraints. So inter-point solvers are aiming at solving problems that look like this one. So you want to minimize f of x, which is a cost function, and you want to respect some inequality constraint phi of x larger than 0. So one thing that you can do instead of solving this constraint optimization problem is that you can penalize violation of the constraint and solve an unconstrained problem. So in this case, it's not really a penalty function. It's a log variable function, but it's going to get a bit more concrete with an example. So I'm taking this very simple example where f of x is equal to x. So this is the objective function that we want to minimize. So if we draw this function onto the graph, we can see it's unbounded below. But when we add this, when we add the constraint to the optimization problem, it's now well defined. So in this case, the constraint is phi of x is equal to x. So we need to enforce x larger than 0. So the orange part in this graph is forbidden. We cannot go here. So in the end, the solution of this optimization problem is located here. This is the minimum. So we can explain what this log variable function is doing to modify the objective function. So I've plotted this surrogate objective function in blue. And you see, so I plotted it for kappa is equal to 1. So kappa is the central class parameter or the relaxation parameter. And as you can see, now the objective is smooth and it's much easier to optimize for such an objective function. It's trying to match the original objective function, so the black line, and it's also shooting out to infinity when the solution is coming too close to the boundary. So this is the case for a large value of the central class parameter. But as we make the central class parameter smaller, this is the behavior that we see. The surrogate objective function is going to try to match as closely as possible the objective function f of x. And at the same time, it's always going to shoot out to infinity when we get too close to the boundary. So what Dojo is doing internally is that it's solving this simple optimization problem where the objective function is smooth and nicely and well defined. And once we have solved this simple problem, we are reusing this solution to warm start a second solve with a smaller kappa. And we do it over and over again until we reach a small value of kappa, typically 1e-4, 1e-5. Yeah. And once you have a solution to the problem with kappa is equal to 1e-5, you have a solution that is extremely close to the solution of the original problem. Yeah, if we look at the KKT condition, I think this is very interesting because this is going to remind you of this box example. So if we want to solve this relaxed optimization problem with some kappa, we have to solve this set of KKT conditions. So to solve this problem, we have to find x, the primal variable, and gamma, the dual variable, subject to some constraint. So this is the first one is the stationarity condition. And the second one is the complementarity constraint. Gamma times phi is equal to kappa. And then at the end, we have two positivity constraints, phi and gamma larger than 0. So in the context of simulating this box, phi will be the sign distance function. Gamma is the dual variable associated with x, but it's also the impact force that you will apply onto the box. And so you might have noticed the single difference between what I've shown in the impact model and this set of equation is that instead of having gamma times phi equal to 0, it's now equal to kappa. So for large values of kappa, I've drawn what this function is doing. So as kappa gets smaller, so as the box gets closer to the ground, we have a larger and larger gamma. So this means that we have a force applied onto the box, and the closer we are to the ground, the larger the force is. So we have forces acting at a distance on the box. So this is not really physical, especially for large values of kappa. But as we make kappa go smaller, we have smaller and smaller value, smaller and smaller forces acting at a distance until we reach something that is almost exactly gamma times phi is equal to 0, the perfect binary switch between being in contact and experiencing forces, and not being in contact and experiencing no forces at all. So this is what is going on internally behind the scene in Dojo, and for this to solve these kind of set of KKT conditions, we are using Newton's method and the predictor corrector mirror choice algorithm, which is I think the state of the art in terms of NTL point solver, and this is enabling us to solve these problems in a reliable fashion, and we can enforce hard contact, very stiff contact, by pushing kappa towards 0 very far, and this is better. This results in linear systems that are better conditioned than primal methods or methods that are implementing soft contact, like Mojoko is doing.
Okay, so we now have a way to simulate hard contact, but how do we actually compute gradients through this optimization problem and through the simulator itself? So to kind of illustrate this with a really simple example, we want to push a block into a goal location. So we're basically going to apply some force, and this is going to move the block off the surface into the air into a particular location. And this example will highlight a bunch of the difficulties and the subgradients that are going to come out of the dynamics of the system. So the actual dynamics of the system are non-smooth. Intuitively, because of gravity, when we push on the block isn't actually going to move off the ground until we apply enough force. So it's not sensitive at all to the force until a certain point, and then we can actually move the block. Now, the gradient of these dynamics is actually discontinuous because of this non-smoothness. So in the middle, you can see that basically the sensitivity of the dynamics is 0. We get to a certain point, and then the sensitivity is 1. Now, these kind of gradients or subgradients are not really useful for a lot of optimization tasks because there's this chattering effect that you'll get. So to overcome this, people typically use finite difference methods. So they'll essentially sample around these discontinuities. This introduces some artificial smoothing that produces some sort of smooth approximation of these discontinuous gradients. More recently, instead of doing finite differencing, these ideas of gradient bundles, which basically introduce stochasticity into the sampling, have been shown to be really useful. So on the right, you can see using a gradient bundle approach where we do random sampling, we start to get some sort of smooth approximation. I think here we used about 100 samples for each point, each of these gradient approximations. And even then, it's still the approximate gradient is still kind of noisy. Now with Dojo in the middle, in magenta, we actually get these really nice smooth gradients at a really cheap computational cost. And intuitively, the way that we control the smoothness of these gradients is with kappa, the central path parameter that Simon talked about, that's related to the log barrier. So basically, as kappa gets smaller and smaller, these smooth gradients will more closely approximate the original discontinuous black gradients. And I guess the other thing to say about this is all of the, for a fixed kappa, this is some intermediate result that the interior point is already solving for. So we have access to all of these results for free. So that is the case for the impact. The same thing, we get the same kind of behavior or characteristics out of friction, whether it's a linearized friction cone or a nonlinear friction cone. So we get these nice smooth gradients that we can use for many tasks. Now, the way that we actually differentiate through the interior point solver is using the implicit function theorem. So in this equation, W is the solution. So this is what the interior point solver returns. What we are actually differentiating through is the residual map or the equality constraints in the KKT conditions. This is R. So basically, the interior point aims to set R equal to 0. And then we're able to basically compute the sensitivities of our solution with respect to any of the problem data. And the problem data here, they can be it can be the state of the robot, it can be the controls applied to the robot, it can be the system parameters like mass, inertia, it can be the time step, the friction coefficients. So we can compute all of these sensitivities. And I guess one really important thing to say is here we're inverting this matrix delta R, delta W. So does this inverse actually exist? And for simulation examples, this matrix typically always exists and is invertible. And we actually already used it. We already factorized it to solve the interior point subproblem for a particular kappa. So it's already factorized, so we can efficiently use that factorization to compute the sensitivities. Now, using these smooth gradients, we can easily perform trajectory optimization. So in both of these cases, we initialize the system with zeros for the control, and using the gradients from Dojo, we're able to successfully push the block to the goal location in both cases. And we did a comparison with Mujoko, which has a soft contact model, which should provide useful gradients. And in the friction sliding case, we found that it did provide useful gradients, but in the case of pushing the block off the ground, Mujoko actually failed, and the finite difference gradients weren't actually useful to ILQR to perform this task.
Taylor, there's a question I wanted to relay, which I think you may have already answered in the formulation, which is, could the contact problem also be solved with a variational formulation?
Okay, so maybe let me rephrase. Could the contact problem be solved in a variational formulation? Is that?
Yes. Mm-hmm.
So I guess the contact problem essentially is solved with a variational formulation. We've sort of abstracted away a bunch of the details which are in the paper. But the way you can think about it is the smooth dynamics of the contact. These all have the variational integrator that we talked about earlier. And then basically the interior point method with its ability to handle inequality constraints is basically handling all the contact. So when no contact is happening, we get all these perfect energy momentum conservation behaviors. Contact is obviously dissipating energy, so conservation isn't there, it shouldn't be there. But yeah, our whole contact model is using variational integrator as well. Okay, so we will quickly just kind of give an overview of some of the examples that we included in the Dojo paper. It's available on arXiv. I think there was a link provided in the seminar. But we were able to perform trajectory optimization using iterative LQR on a bunch of interesting systems. So on the left, this is kind of a Raybert-inspired hopper. And the task is to literally just hop to a goal location. So the optimizer has to figure out that it needs to break contact with the ground to hop to a new goal location, which is able to successfully do. On the right, this is the Unitree A1 robot. Here, we basically designed a nice kinematic trajectory that's dynamically infeasible. And then in the cost function, we basically regulate to this kinematic plan that we like, and LQR is able to find dynamically feasible plan that looks really nice. And this is running in just a couple of minutes on pretty standard workstation. We took the same idea and applied it to Atlas with no arms, and we're able to get these nice walking behaviors out. And again, this is taking maybe 10, 20 minutes again. And then we can use the gradients to optimize smooth plastic systems like the cart pole in order to do a swing up in the bottom right. We also use Dojo to optimize policies for locomotion using reinforcement learning. So on the top, this is an ant environment similar to the gym environment. On the bottom is the hack cheetah. And we trained static linear policies, which means we just have a single linear matrix that's doing feedback. And we optimize this using augmented random search. And we get these nice behaviors. One thing that we did as an experiment for the paper is to use the gradients from Dojo to hopefully make the training more efficient. So augmented random search is basically a derivative-free algorithm that basically just computes the rewards for a given simulation rollout. And then we compared that with what we call the augmented gradient search, where we compute the gradients from Dojo and then use those to update our policy parameters. And what we found in these experiments is that we can train pretty comparable policies way more sample efficiently using the gradients from Dojo.
Yeah, another application that we have looked into is system identification. This can be really useful if you have a robot that is interacting with its environment. It's important for the robot to be able to build accurate models of its environment to then act in this environment and make and break contact with objects in objects around the robot. So you would want to be able to learn accurate models, like learning friction coefficient for objects that are surrounding the robot. So this system identification task is trying to get at this kind of behavior. In this task, we are given a data set of box tosses. So we have this box which is tossed on a table multiple times, and the trajectory is recorded using those April tags. And then our task is to recover a correct model for this box. So recover the geometry and also the friction coefficient. So yeah, to learn a contact model. And this is the result that we have. In orange, we have the ground truth trajectory that is in the dataset, and in blue, we have the learned model that we learned from the box tosses. It's not perfect, it's not perfectly accurate, especially with respect to the friction coefficient. You see that there is a bit more sliding for the ground truth, but the result is pretty accurate, especially considering that we are trying to learn the geometry of the object. So we start with some initial geometry, which is randomly initialized with an initial guess that is way different from the actual geometry of the object, and we are able to identify this geometry just from the trajectories and recover the cube, the shape of the cube, pretty accurately. On the other side, you can see the friction coefficient. So here we are showing the friction cones, and in orange you have the ground truth, and in blue you have the friction coefficient that we learned during the optimization phase. And so you can see it's converging to something that is quite close to the original friction coefficient. I'm not going to dive too much into the details. I don't think we have time for this, but all the details are in the paper. But basically, for this system, we have just a simple cost function, objective function that is trying to match what happens in the simulator and what happens in the real world data. And to optimize this objective function, we need to compute its gradient, its Hessian. And to do this, we are leveraging Dojo's gradient multiple times. So yeah, I think now we have shown all the applications that we have been worked on so far. Maybe there is a question. We can take a question now, or we can switch to the live demo.
Thank you so much, guys. This was an amazing talk. I think you guys did a really good job of explaining for not as familiar with it. So thank you. I think I just have one quick question, and then if there's any more, we can continue. So in here, did you say that you use like multiple values of kappa and you keep producing that value?
I didn't catch what you said. I'm sorry.
Sorry. So in the interior point solver, are you using like do you reduce the value of kappa?
Varun, there's some disturbance on the line, which I'm not sure anyone else is experiencing, but I certainly, when you speak, there is a buzzing sound that makes it.
Sorry about that. Let me go and find a note. I'll save my question later.
If you can type it, I can speak it out for you.
Mm-hmm.
I was wondering if Dojo has just the sort of basic support for like URDF loading and visualizers around it and so on.
So, yeah, so there is a URDF parser in Dojo, so you can provide a URDF, and this will build the mechanism in Dojo, and you can then simulate it. And this will also visualize the robot with the associated meshes, with the meshes associated with the URDF. So this is implemented.
We have the question from Varun, which is, in the interior point solver, do you start with an initial value of kappa and reduce it iteratively?
Yeah, so we start with a pretty large value of kappa, typically a value of 1. So this is extremely smooth dynamics and extremely having a lot of forces acting at a distance, and then we crank down on this value using the predictor corrector algorithm, which is going to schedule this decrease in kappa in a way that's trying to be optimal. So it's an automatic scheduling scheme for this kappa.
Yes, I had a follow-up question, which is, as you reduce kappa, the conditioning of the problem from an optimization perspective perhaps gets worse. And I was wondering, when you connect this with trajectory optimization, if there's some sort of sweet spot where it's still a little bit soft, but it makes the job of the optimizer easier.
Yeah. So I guess to answer the first part, basically, with a primal approach, it's often really difficult to make kappa get close to zero because the conditioning gets really bad. Kind of intuitively, Mujoko is a primal method, and that's part of the reason why their soft contact model can't really converge to hard contact because the problem gets ill-conditioned. What we're doing and what the Morotra predictor corrector algorithm is doing, it's a primal dual approach, which means the problem is better conditioned. And that doesn't mean that the linear system isn't necessarily ill-conditioned, it is. But in practice, this is part of the beauty of interior point methods is that they can still be reliably solved to really good tolerances. And to answer the second bit of the question, is there kind of a sweet spot, like what value of kappa should you pick to get good smooth gradients? And I think the optimal kappa, we don't have a good way to get the optimal kappa. It's probably a bit problem dependent. In practice, what we're finding is kappa about 1 e to the minus 4, 1 e to the minus 3. This is a really good value. And this is what I think we used 1 e minus 4 for all the trajectory optimization examples. So it's not like something we had to tune individually. We just sort of set it, and this worked. And I think if we showed those smooth gradient plots, I think the 1e minus 4 kind of intuitively is what you would probably pick.
If there's no more questions in the immediate, maybe we can switch to the live demo and then come back at the end.
Yeah, that sounds great. So yeah, we are going to start the live demo. Hopefully you can see the screen. This is a Jupyter notebook with some Julia code implementing the augmented random search. We are going to try to train a simple agent. So half cheetah, the robot that you've seen earlier in the talk, try to get a walking gait or running gait with this environment. So we start off by loading some packages, especially we are loading Dojo and some usual packages like linear algebra in Julia. And we are also including here the augmented random search algorithm, which is extremely simple. It's trying to learn a linear policy. So a very low number of parameters, and at the same time, yeah, the code is very simple. It takes maybe 100 lines of Julia to write it down. So now we're going to start the training. So we first create the environment using this get environment method, and we specify the environment type, which is going to be half cheetah in this case. And we are going to be simulating this robot at 20 Hertz, so a pretty large time step of 0.05. Next, we want to create this policy. We are going to initialize it at random. So we have some hyperparameters. So we are going to first define the hyperparameters of this augmented random search algorithm. So the main loop size is just the number of episodes that we want to, the number of training steps that we want to take. The horizon is the length of each episode. So it's there are 20 time steps per second. So 80, and the horizon of 80 is corresponding to 4 seconds of simulation. And then the number of directions is the number of samples that we take to evaluate the gradient of the dynamics in a stochastic fashion. So we are just taking 6 directions, and then we are trying to fit a gradient to those six values, 6 samples that we've taken from the dynamics. And then the step size is just some kind of learning rate for the augmented random search. So yeah, then we need to create this policy and initialize it at random. So the policy is just going to be a matrix of size input times output, and the input size is going to be the size of the state, and the output size is going to be the size of the controls. And we have a normalizer object which is going to look at all the state that we visit and try to renormalize the state so that they look like white noise. So yeah, basically the augmented random search works this way. The policy at least works this way. We have a normalizer that is going to normalize the state X that we observe at the moment, and this is going to give us X bar. Then we have a linear static policy. So we have one theta for the whole policy, which is going to be mapping the normalized state into a control. So the policy is really simple. It's just theta times the normalized state. And what we end up with is a policy which is parameterized by this single matrix of size 14 by 18. So 14 is the number of controls, and 18 is the number of state in this example. So we have 100 parameters only. Okay, and then we can start training. And so this is going to take a bit of time. So maybe we switch to a second demonstration, and we'll come back to it to look at the results and look at the policy that we got out of this.
Okay, so so now we're going to show off a just simulation result. So we're basically going to take that unitary A1 quadruped robot. We have a URDF. It will basically get loaded in, and then we'll drop it and simulate it and visualize it in the visualizer. So again, we're just going to basically activate the package. This is super similar to basically activating some sort of Python environment. Okay, so that loaded. Basically, when we call instantiate, this basically pulls any Julia packages that are needed in case they're not already installed. We're going to use Dojo, so load in the simulator. We can set all sorts of parameters for this environment. So we can set the gravity, we can set the time step, we can set the friction coefficient. This is typically a value between 0 and 1, or maybe 0 and 2. We can set damping for all of the joints. And then we can, the same way that we got the half-chain environment, we can get a quadruped environment. So we can also pick a representation. So Dojo behind the scenes is simulating everything in maximal coordinates, but we have a bunch of nice efficient code that will automatically convert from the maximal to minimal representation and from the minimal to maximal representation. And all of these gradients are already defined. So we'll set the time step. We can turn on contacts on the body, and then we'll set the rest of these parameters. So then to simulate, all we're going to do is we're going to initialize the mechanism. We're going to tell it it's a quadruped, and then we're going to set the position to be 0.5 meter in the air. And then we have a simulate method where we take in the environment's mechanism. We're going to run the simulation for 2 seconds. We're going to record the output into the storage object. And then you can set interior point solver options. Typically, the user doesn't need to tune these parameters at all. We just want to show that you can set them pretty easily. In case anyone is unfamiliar with Julia, this exclamation point, it just means that an object that's being passed into this method is being modified in place. So that object will be different after this method is run on it. We can load the visualizer. So this is, we can interact with it. You can move it around, spin the object. We can reset it. So you can see the quadruped is up in the air. all of these red circles, these are the contact points. So currently Dojo supports sphere and capsule contacts. We're not supporting convex shapes or meshes yet, but that should hopefully be coming soon. So then we can actually run, or we can visualize the simulation. So if I click play, it drops the robot on the ground. And then the visualizer has nice GUI support so that we can move around the trajectory. We can also slow down the simulation and watch it in slow motion. So here it's running at a tenth the speed. We can see we have nice, perfect hard contact. Yeah, okay, so that is a pretty standard workflow for any sort of robotic system that we want to simulate. So the next thing that we'll show is we'll show trajectory optimization for the block example that we demoed in the talk. So as before, we'll load all these methods. Here, the only difference, we're going to load in iterative LQR. This is a really fast implementation of IOQR that will automatically use Dojo's gradients. So we can load that in. As before, we're going to get environment on our block. Here we can represent the system in maximal coordinates. For a single rigid body, this is the same in maximal or minimal coordinates. So we loaded in the environment. And then, so we'll refresh the visualizer, come back to this after we run everything. We can get the dimensions of our system. So here n is the state dimension, m is the number of inputs. We can define initial and final states. So these are just vectors. Z1 is the initial state. So it basically has the first three values are the position. So we're going to start at quarter meter in the air. That's the center of mass. So basically it'll be sitting perfectly on the surface. And then the goal location is going to be 1 meter away in the y direction. We can set a horizon for the problem. So we'll just optimize over 11 time steps. Here, we're basically setting the dynamics. We're giving the dynamics to IOQR. So you can see that we basically load in the Dojo environment. And we're able to set up a trajectory of dynamics models for each time step that's given to the optimizer. So now we can basically initialize the system with controls. So U bar, this is going to be just 0 controls. We're not giving the optimizer any guesses what it should do. And then we can roll out the dynamics. So we'll take in the model, an initial state, the control gas, and then this will visualize. So if we go back up to the visualizer, we can see the initial guess didn't do anything. It put the block on the surface as it should have been, and it didn't do anything. It hasn't moved at all. So we can now define an objective. So basically we define a stage cost OT, basically just quadratic on deviations from the goal. And then we have quadratic costs on the controls, which are a bit smaller. And then we have a terminal stage cost, which is the same as the stage cost on the states. And then here we just generate these cost function objects and then generate a trajectory of costs that will form the objective. For the constraints, we define a goal constraint, which is basically we want the final state to be equal to ZT. And then similarly, we define a trajectory of constraints for the optimizer. And then for the actual, for the optimizer itself, we pass in the model, the objective, the constraints, and then there are a bunch of options. I think these are pretty much the default options. We can initialize the controls, we initialize the states. So now we have instantiated a solver, and then we can call solve on the solver. I think it's running a little bit slow because we have RL training in the background. So we can basically recover the solution. So we're basically going to get the trajectories from the solver, Z and U. So we can look at all sorts of information here. So the final objective value is, about 15. It took 30 iterations, and the error between the final state and the goal state is 3e minus 3. So pretty good. And then we can visualize the system. So basically just going to grab the trajectories of the states of the controls. We'll visualize the system. We're also going to visualize the control input force. And then we'll just set some, we'll set the camera position and we'll set the floor so that everything looks nice. So then if we come back up to the visualizer, we can reset, we can play, and we can watch the force push the object. So we can watch a little bit slower, I guess. And this is, you can see the basically the position and the magnitude of the force that's needed to push the block to the goal location. Yep, and that's it for this example. So pretty straightforward workflow. And this is the same workflow we're using to optimize the quadruped gates, the Atlas gates. Yeah, so I'll hand it back over to Simon. Hopefully the RL trained.
Yeah.
Hopefully I talk slow enough.
I think it's not ready yet. So maybe we can take questions and go back to it later, or we can abort and show like the policy I trained right before this session. So maybe I can just show the result that I've got earlier today. So this is once you have trained the policy, you can compute the trajectory by just rolling out the policy on the system, and then the next step is to render or to visualize the environment and set the camera. So this is the result that we've gotten from this policy. It's clearly not the most efficient policy we've seen on half cheetah, but this is pretty decent result. Yeah. So I think that's it for the presentation of this RL example. If it finishes before the end of the talk, then we can showcase the result too. But we are happy to take questions if you have.
So Varun has a question on going into more detail on the different types of gradients, for example, subgradients, gradient bundles, and so on.
Yeah, sure. So yeah, there are plenty of there are different types of gradients. So yeah, the most obvious one is the finite difference gradient, where you simulate the dynamics. So say you want to differentiate the dynamics with respect to the input or the controls that you apply on the robot. So you want to differentiate the state at the next time step with respect to the controls. You're going to first simulate once, and then simulate for many different controls around your current control to be able to compute this Jacobian. But this is going to be computationally very intensive because it requires to solve many times pretty much the same problem. There is also the gradient bundle approach. For this one, instead of sampling deterministically around your current control, you're going to sample in a stochastic fashion. And maybe, so what has been proposed is to use some Gaussian noise to add some Gaussian noise to your control and sample this control. And once you have many samples of your dynamics, you're trying to fit the gradient that is going to best match all the samples that you've taken through the dynamics. So those two methods are typically very computationally intensive. For the subgradient part, for the subgradient method, I think this is the gradient that you get out of auto differentiation techniques. And also, this is the thing that has been proposed with the dart simulator, for example. And so, for the subgradient, it's computing the exact gradient of the stiff contact, of the stiff impact. And so, as we've seen in these slides, the gradient of those stiff impacts is going to be like this step function. It's going to be very myopic in terms of providing information about the landscape, the dynamics landscape. So it's not going to be very helpful. On the other side, it's also very cheap to compute. It's as cheap as it can be, as cheap as the gradient that we compute with Dojo, but it has some drawbacks, which is being myopic. In a way, it's not by considering like very stiff impact. It's not considering contact that might happen if you slightly change the control. It's only considering the active contact at the current time step. It's not going to reason about objects that are approaching your robot pretty closely.
I had a question about the robustness of the gradient calculation if you're not close to the local min, because strictly speaking, if you're not at local min, the IFT does not hold, right? It won't give you the right gradient expression. So.
Yeah, so that's a really good point. So I think to sort of restate what you said, basically, if R is not 0, then do you still get good gradients? And honestly, I think this is something we haven't really experienced that much, because with the primal dual interior point solver, we can pretty much always drive R to be the infinity norm is about, in the worst cases, 1e minus 4, 1e minus 5. And so in that case, the implicit function theorem works really, really well. Yeah, I guess we can't say that much more about like R being too big.
Yeah.
This probably won't work that well. And in the case of Dojo, I guess what we would do is, let's say the R failed for a particular value of kappa. We could still use a value of kappa previously that succeeded. I guess actually, maybe even if the R is still big and we can't make it small, that means the simulation step failed, which means there's probably no point in trying to compute the gradients if the simulator has failed.
Yeah, it's going to be unreliable, I would say. Yeah, if we didn't converge on the residual.
I had one more question about can we expect like real-time speed so that this can be part of an MPC policy?
Yeah, so I think currently the version, the code is in its first version. It's not as fast as we would wish, but we are working on a second version and making it much faster, relying on the fast Julia implementation. In terms of implementing this in an MPC loop, I think this we can simulate. We should be able to simulate all the systems that we've seen today in real time or faster than real time. But when it comes to MPC, you not only have to simulate in real time, but you need to be about 10x faster or maybe 100x faster to be realistic. So I guess in this context, it would be maybe a bit tricky to do it with Dojo with the full nonlinear dynamics everywhere, nonlinear contacts, nonlinear sign distance function. But if you linearize all of those quantities, the contact and the friction, the sign distance function, the dynamics, what you can do, I mean, I guess this should be feasible, and this is what we are doing with a previous work that we've done together with Taylor. This is the CIMPC work, so contact implicit MPC, where we have a reference trajectory that we want to track. And so to track this reference trajectory, we are linearizing the free-floating dynamics of the robot. We are linearizing the sign distance function, all the contacts. And then with those simplifications, we are able to run an MPC loop at real-time rates but yeah, I think we are not ready yet to do the full nonlinear thing, especially in real time.
Yeah, I think in terms of the algorithm, I think the algorithms are all stabilized and really good and reliable now. I think what we need to make Dojo fast enough for real-time NPC is a team of like 5 to 6 good software engineers and 6 to 12 months basically. And I think that this could be feasible.
Super exciting. I think we just have a couple more minutes left. So are there any other questions? Varun asked me to, before we close, to share perspective on where the field is headed, open challenges to address, any other thoughts or insights. Well, I mean, I think the simulation, when combined with real world data, so that you actually take the simulator, learn the parameters, and then you can parameterize dynamic aware policies, where these policies are making decisions from pixels or other kinds of very raw inputs. So in other words, like I'd love to see a differentiable simulation engine coexist and play really well with all the large scale learning tools, so that the simulation quality improves, becomes more and more realistic. And yeah, we can get like data efficiency coming from dynamics awareness. And I feel like a lot of work has to be done still to get the scale and the speed and the realism. So yeah, that's sort of a long-winded answer to open questions. But I think this is the first talk I've been where not only was the theoretical material very well presented, but also you dared to actually train a whole RL policy as part of the talk, which was amazing. So yeah, thanks for sharing this really exciting work, and I'd love to see where the next steps that the simulation work takes. So thank you all for joining. It's 12:30, and with that, we'll close the talk.
Thanks everyone for joining. Have a good rest of the week.
Thanks.
Thanks, Varun, for organizing all this, and thanks, Vikas, for sharing the session. This is really an incredible opportunity for us to talk about the research. So thank you for this.
Absolutely.
Great to have you.
Bye-bye.
Bye-bye.